Hello, everyone, and welcome to our Flotation webinar. My name is Scott Martin, and I am the Sales Manager of the Americas for Glencore Technology.
And I'm Rebecca McKechnie, Senior Solutions Metallurgist for North America. I'm excited today for two reasons. One, my upcoming move from sunny Brisbane to Toronto, right in the middle of winter. And two, for you to listen to our Senior Metallurgist, Carter Lawrence, discuss the Jameson cell. This is a flotation technology that set new standards in efficiency and performance.
Today, we'll compare the Jameson cell with various flotation technologies, including conventional cells, column cells, NovaCell, direct flotation reactors, reflux flotation cells, StackCells, and Concorde cell. Carter will highlight how the Jameson cell's unique design and operating principles contribute to superior recovery and reduced operational cost.
So whether you're looking to improve your existing circuit or explore new technologies, this session will provide you with valuable insights to help you make informed decisions. Now, during the presentation, ignore the raise hand button and instead just use the Q&A button for any questions that you might have. And you can ask your questions at any time during the webinar. So let's get started.
Okay, thank you. So the webinar today is going to be called Flotation, Comparing Available Technologies, and we're going to be looking at basically doing an overview of various flotation technologies and their applications. So the flotation technologies that we're going to be covering in this webinar include Jameson cells, mechanical cells, the Concorde cell, NovaCell, StackCell, a column cell, direct flotation reactor or DFR, the Hydrofloat, and the reflux flotation cell or RFC. Now the various areas that we're going to discuss are the principles of operation of each technology, the history and installations, process optimization and control, operational ability and flexibility, some capital estimates, electricity and consumables estimates, estimates of various footprints, the test work options for each technology, a little bit about the evolution of the Jameson cell, and a final summary. Now, just a small disclaimer is that all the information presented in this webinar is from publicly available sources and is current at the time of writing. So I'll now give a brief overview of how each technology works. So I encourage viewers to contact the OEM of the respective technology or Glencore technology if you have further questions about the operation of any of these cells. So the first up is the Jameson cell. So the Jameson cell uses a downcomer and slurry orifice as the heart of the cell. So pressurized slurry enters the downcomer through a nozzle at a high velocity of 17 meters per second. Then the jet entrains the air in the headspace, which creates a vacuum inside the downcomer and draws the slurry up into the downcomer. The jet plunges into the slurry surface, causing your entrained air to shear into very fine bubbles. And then you get very high intensity mixing, which leads to high probability of bubble particle collision and contact. The residence time in each downcomer is only several seconds, and there's no external air blower or supply required. The next up is the mechanical cell or tank cell. With the mechanical cell, the slurry is either pumped or gravity fed into the bottom of the tank. Forced air and mechanical agitation is used to create particle and bubble interactions. And target minerals attach to the bubbles and rise to the top where they're collected in collection launders. Next up is the Concorde cell. So the Concorde cell has a similar appearance to the Jameson cell, as both were developed by Professor Graham Jameson and were tested and owned by Glencore Technology. However, its key mechanism is the blast tube. It has the potential to generate smaller bubbles if operated at higher feed pressures than a Jameson cell, and enough frother is added to maintain them and stop them from coalescing. Slurry discharges from the blast tube through a choke into an impingement bowl in an attempt to reduce the high energy or velocity entering the tank. An increased slurry velocity means that it requires an air blower system instead of naturally entrained air. Now moving on to the NovaCell, which is another creation from Professor Jameson. Now similar to a Concorde cell, the NovaCell features a blast tube. It features a fluidized bed within the tank, which creates a less harsh flotation environment. This influences the probability of collection of coarse particles, which can be collected from a middling stream featured in the middle of the cell. It aims to collect both fine and coarse particles, but the overall aim is for coarse particle recovery. Now moving into the column cell. The column cell eliminates the need for mechanical agitation by increasing the height of the cell. Taller flotation columns allow for increased residence time, increasing the probability of bubble-particle interaction. Fine bubbles are generated within spargers at the bottom of the tank, with feed slurry entering above the bubble generation zone. Now into the StackCell. The StackCell is a mechanical cell, but it's a two-stage mechanical cell that features an internal contacting chamber, which is shown here. In a normal mechanical cell, you will agitate the entire cell volume, whereas the StackCell is isolated into mixing just inside the contacting chamber. This increases the intensity of the bubble-particle interactions and reduces the turbulence of the separation zone to stabilize the froth phase formation. And it also reduces the residence time, and therefore cell volume required when compared to conventional cells. Now we move through into the DFR, or direct flotation reactor. Now the DFR aims to eliminate the froth phase entirely and froth slurry interactions. It's a completely pressurized unit, which removes dust, off-gas, or mist exposure risks. Loaded bubbles are recovered through the top piping of the reactor, with tailings exiting via port on the side, which is shown here. And DFR units can be installed on the same level in trains, and they don't require a step design, reducing the overall height of the circuit. Now the reflux flotation cell, similar to the DFR, the reflux flotation cell is a frothless cell, and it aims to recover particles before forming a froth phase. It utilizes the boycott effect, similar to a reflux classifier, to separate gangue from the valuable minerals. The inclined channels, or lamella plates, assist in the rejection of gangue particles rising back into the cell. And the Hydrofloat. So the Hydrofloat is an aerated fluidized bed separator which is designed specifically to target coarse particles. It differs quite significantly from traditional flotation technology, only suitable for particles above 150 micron. However, it can also float particles much coarser than traditional flotation technology. The key principle of design is that your gangue particles will remain inside the fluidized bed shown here, while your coarse target minerals will float to the top. It's a much gentler and lower shear environment when compared to traditional flotation methods, and this allows for coarser particles to be collected without risking detachment. So we're now going to move through into a table of the history of the flotation technologies. So what we've done is broke this down into three different categories of green, orange, and red. Now, your green category will have more than 25 years experience and more than 100 installations. So that includes the Jameson cell, the column cell, and the conventional cell. Orange is for 10 to 24 years experience in the industry and 20 plus installations. So that's your Hydrofloat and your StackCell. And then the red technologies have less than 10 years experience and less than 20 installations, which is your remaining technologies. And you'll see that some have only one or even no commercial installations. Now moving into the process optimization and control for each technology. So we broke this down into four key categories. First, we have the tailings recycle system, which recycles a portion of your tailings back to your feed, and that'll be discussed further on the next slide. Now, only the Jameson cell, the Concorde cell, and the column cell have a tailings recycle system. You then move into air control. Now, air control is absolutely essential for flotation, so you'll find that every flotation technology has some form of air control. Then we move into level control, which is the ability to control the froth depth or the amount of, or the level of the pulp inside the cell. Now you'll notice that the DFR and the RFC are both red. This is because they are frothless cells, so there is actually no froth level to control. We'll discuss on the next few slides what the implications of that are. The last is a wash water system, which essentially uses clean water to produce a cleaner concentrate and improve concentrate grade. Only the conventional cell and the Hydrofloat do not have this system. Now, tailings recycle, so why is it important? Well, the main benefit of a tailings recycle system is that it will maintain stable operation in a flotation circuit despite any upstream process disturbances. So that means you're going to have less downtime, less maintenance issues, and less operator intervention required. Additionally, a recycle system will give any particles that are not collected on the first pass an additional chance to be collected. This is especially important for flotation cells with separate contacting chambers. An example of this is the StackCell and the Reflux flotation cell. In these technologies, there's no mechanism to capture particles that have not been collected in the separate contacting chamber or that drop back from the froth. This will then increase the risk of recovery loss. Now, frothless cells, how are they different from traditional cells? Well, frothless cells, such as the DFR and the reflux flotation cell, they seek to recover the concentrate before you form a froth phase. So the main benefit of this is that you end up with a more compact footprint of your cell, and you require less area for froth formation. A secondary benefit is that there's less drop back risk from the froth because you are recovering the material at an earlier stage. However, the trade-off of removing that froth layer is that you also lose some process control. So your grade control becomes only realistically possible through wash water addition. So you're then potentially limiting the maximum upgrade potential in a cell because you don't have the drainage that you get with froth. And second is that the cells are completely enclosed, and it removes the ability to visually troubleshoot as well as use any automation features such as froth cameras. You will find in most concentrators that operators rely on visual inspection of the froth to quickly and easily troubleshoot problems, and you are removing that ability with this technology. Now, another area we looked at for process optimization was the separation zone turbulence inside the cell. Now, once your particle bubble interaction has been achieved, it's important to reduce turbulence in the separation zone to not cause particle detachment. Now, ideally, this means you keep the particle bubble interaction in a separate contacting chamber before transferring into a more stable separation zone. Now, you'll notice on the table on the right here that we have the conventional cell, the Concorde cell, and the direct flotation reactor as red for that separation zone turbulence. The reason for that is the DFR and the conventional cell don't actually have a separate contacting chamber. Everything gets mixed in one chamber. So that results in a higher turbulence inside that separation zone and increases your risk of particle detachment. Now, the Concorde cell is also red even though it features a separate contacting chamber, and the reason for that is it uses very high amounts of energy, which force the slurry out of the mixing zone and into an impingement bowl, which is shown here on the diagram, at very high speeds. There's also a choke at the bottom of the blast tube to allow level to be maintained in the blast tube at high air-to-pulp ratios. And these factors result in a high velocity exiting the blast tube. And the result of that is it likely increases the risk of particle detachment. Even if you collect additional particles in the blast tube, you're then risking detaching them when they exit at that high velocity. And the result of that is that you then require higher tailings recycle rates to try and avoid recovery losses. So we're now moving into the proven operational ranges for flotation technologies. Now, the ranges you'll see at the top of ultrafine, fine, coarse, and ultra coarse, those particle sizes are based on copper, but they will be applicable for most base metal and precious metal applications. For things like coal, the ranges will be a lot more coarse because of the low density. Now, you'll notice on this table we have, again, the green, orange, and red. We've also added a gradient green for this one, which means that the manufacturer has claimed that particle size range will be able to be recovered, but they don't have the commercial installations to essentially prove it. Now, we'll move into sort of break it down so the table's not so big and bulky. We'll have a look at the fine particle ranges for the flotation technologies. So the first table looks at ultrafine and fine flotation. Now, for the ultrafine flotation, the Jameson cell is the most established and proven technology. The Concorde cell and the reflux flotation cell also appear to be viable options, but they are far less established and proven. You'll see that the reflux flotation cell again has that gradient green color, meaning that it does not have the commercial installations yet. And I believe the Concorde has around 1 to 2 commercial installations. Now, the column cell, the DFR, and the StackCell are both yellow in this table. And this is because it was not clear whether ultrafine performance would be in line with the high-intensity cells that we just mentioned before, but it is expected they would have superior performance to conventional cells. We then move into the coarser particle ranges. So coarse, and we call the additional category of ultra coarse. So that's where you get into above 350 micron particles, very coarse. Now, for general roughing duties, most flotation technologies will be suitable. However, you'll notice again that many have very limited installations, and those are marked with the gradient green table again. Now, for coarse particle flotation or just general roughing, conventional mechanical cells are the most established and proven technology. However, the Jameson cell is also a very well-established alternative with about 80 installations in roughing and scavenging. Now, for ultra-coarse flotation, the Hydrofloat is your only proven technology. However, the Hydrofloat is only suitable for particles above 150 micron, and it does require removal of particles below this size, which does have implications on footprint, water consumption, and capital cost. Now, the NovaCell is aiming to compete in the same market space as the Hydrofloat without requiring that fines removal, but so far it's still relatively inexperienced in the market and does not have any commercial installations as of yet. Glencore Technology is also investigating a coarse particle flotation technology at the piloting level currently. Now, we're moving into the proven operational duties for each technology. Now, the 4 duties that we've chosen are a rougher, which is just your standard rougher duty, a scalper, which is the ability to produce a final concentrate from either flotation feed or cleaner feed, a scavenger, which is a high recovery cell, or just a general cleaner cell. Now, again, we've used the gradient green color, which indicates that the OEM claims that technology would be effective in that duty, but there's no full-scale installations to back it up yet. Now, a couple of notes. We did mark the Concorde cell yellow for scalping because it's only suitable for very fine particles, so rougher scalping duty likely won't suit. The NovaCell requires coarse particles to operate, so only rougher scalping would be suitable, and that's why it was yellow. The column cell was also marked yellow for roughing because it's known that column cells may struggle with coarser particles. So we'll now move into making a capital estimate for flotation technologies. Now, all manufacturers keep their pricing private, so what we are doing is comparing a few factors that will go into what drives capital costs in a flotation circuit, and then making an estimate comparing the flotation technology to a conventional circuit. We're not doing it on an individual cell basis, we're doing it on a circuit basis, fully installed. So the first thing we're looking at is, are any premium materials required in the equipment, such as stainless steel? Obviously, premium materials will drive up your capital cost. And for the Concorde cell, the NovaCell, and the Reflux flotation cell, there are some stainless steel parts needed, which will drive up the cost. We then look at the auxiliary equipment required, so things like pumps, air blowers, agitators, these will all drive up the cost of the equipment. We do note as well that certain equipment such as high-intensity cells like your Jameson cell, your Reflux cell, your Concorde cell will have higher pumping requirements than, say, a conventional cell, and we do take that into account. Some other considerations are things like height of the cell or maintenance clearance for agitators. One note for the Hydrofloat is it does require removal of those sub 150 micron particles, which will increase your footprint requirements and water consumption. Now, we then looked at, does the equipment rely on residence time? And why that's important is that technologies that rely on residence time will require higher volumes and therefore more units. So while they may be a smaller or cheaper option for a single unit, when you look at the fully installed circuit, they often can cost more. I have noted that the Concorde cell and the NovaCell are marked yellow for relying on residence time. The reason why we said yellow was that those cells have the blast tube technology and use very high pressures and high velocities inside the cell, And so your tailings recycle rates are going to be higher, which is going to drive up your equipment sizes and the cost. So this is the final where we've arrived at for comparing the total installed capital costs versus, let's say, a conventional rougher scavenging circuit or a full conventional circuit. We said that the Jameson cell would come in lower. We obviously didn't compare a conventional circuit to itself. We said the Concorde cell would be similar because they do require mechanical cells to recover coarser particles. So in a rougher scavenging duty, they would require mechanical cells in addition to the Concorde cell. So we said similar capital cost. The Hydrofloat and the NovaCell, we declined to make a comparison because they are specifically targeted at coarse particles. So they are a little bit of a specialized duty, and they often would be in addition to a conventional or traditional flotation circuit. And then your frothless cells, your DFR and your RFC, they both came in lower as well, and your StackCell came in lower because it is a much smaller cell than a conventional cell. Okay, we'll then move into the comparison of the expected electricity and consumable usage. So we again, the same as the last table, we looked at what consumes electricity and what consumes spare parts on the equipment. Again, pumps, agitators, air blowers will all consume electricity at varying degrees. We then added a category for this one on how much pumping is actually required for an individual technology. So for a Jameson cell, for example, we said that would be a moderate requirement because there is moderate pressures required, and the pumping required will be higher than, say, a conventional cell. For the Concorde and the NovaCell, we said they would be high because the pressures are higher than a Jameson cell. So you're going to require larger pumps and more pressure. We then looked at whether the equipment has moving or internal parts, as this will affect the availability and whether you need to actually shut down the equipment to do maintenance, and it's also just more parts that need to be changed. So the Jameson cell, obviously, it does not. The most common internal moving part is an agitator, which is found on multiple of the technologies, and that will increase your electricity consumption and your maintenance costs quite considerably. Again, we looked at whether the equipment relies on residence time. And we also looked at, do those consumable parts that have to be changed have premium materials on them like stainless steel? And what we did then was we categorized the electricity consumption based on a prediction of low to moderate to high. And so for the Jameson cell, the Hydrofloat, the column cell, and the Reflux flotation cell, because these don't have internal or moving parts, we ranked them as low. The Concorde cell, the NovaCell, the DFR, and the StackCell were moderate. The StackCell and the DFR, despite having agitation, they will be a much smaller agitator than a conventional circuit. So that's going to drive down your electricity consumption considerably. And then your conventional mechanical cell comes in the highest because they are very large volumes with large agitators. The electricity cost is quite high. And we will talk more about that a little bit later on. We then looked at the spare parts consumption and cost as well. To be honest, all of these came in as the same as the electricity consumption because we looked at whether they had, again, moving parts, premium materials required, and ranked them on that basis. So we then moved into comparing the footprints of these technologies. And this can be difficult to do as well because you don't want to compare a single cell to a single cell because you need to look at a respective duty. And so what we did was we took a basic mechanical rougher scavenger bank that would be 6 70 cubic meter flotation cells. And we used available information on the Jameson cell to calculate what the Jameson cell reduction in footprint would be to compare. And then we compared all the other technologies to the Jameson cell to see where they sit. And what we found was that the Concorde cell, the Hydrofloat, the column cell, and the NovaCell came in higher, as well as the StackCell, where your frothless cells did come in either similar or lower. And we will have a bit more of an explanation on the following slides on why that's the case. So a bit of an explanation around the Concorde cell footprint. So despite looking similar, the circuit design for the Concorde cell differs quite significantly from the Jameson cell. Now, there is an ultra-high shear environment, which likely reduces the recovery of the mid-size and coarse particles, which we have already discussed. Now, the resulting Concorde flow sheet is therefore going to require mechanical flotation to achieve your overall recovery. So you can see on the flow sheet here that you have Concorde scalpers recovering your ultrafine particles at the front, but then you have the mechanical cell scavengers at the back end. Now, this unfortunately will drive up the footprint required and increase your capital costs. And we do have a published paper from Metso Autotech which support this hypothesis if you'd like to check it out. Now, the DFR and the RFC, while we've discussed a little bit about frothless cells, this is a bit more of an explanation. The individual cells, because they're frothless, are quite small, but this reduction in size does come at a cost of process control. Now, the difference between the two is that the RFC has a high-intensity mixing zone and is not mechanically agitated, where the DFR is mechanically agitated. So it's going to drive for the DFR, you're going to need more clearance above it for that mechanical agitation. Neither of the technologies has a tailings recycle system, which means that they can sit closer to the ground, but at a cost of process stability and possibly recovery, as we discussed earlier in the presentation. So the result is that the RFC will theoretically have the lowest footprint of all of the technologies discussed, but there are currently no commercial installations to confirm this footprint or its performance. Now for the StackCell aims to be a much smaller version of a conventional cell, so requiring less volume and residence time. And it has definitely achieved this, resulting in a significant reduction when compared to conventional mechanical cells. However, it does still rely on the same principles for sizing as a conventional cell. So it means that you need multiple units for a duty to achieve adequate residence time. You need them to be stepped. You need clearance for mechanical agitation. And all of these things will drive up your footprint, which means that it does still end up with a larger overall footprint than the high-intensity cells, such as the Jameson or the RFC, but it is still quite a significant reduction from conventional flotation. So we'll now move into the test work options for each technology. Now, most technologies are going to have lab scale, pilot scale, and demo scale test work. There was a couple boxes that we marked gray here because we just weren't able to find any publicly available information and we didn't want to make assumptions. Another category that we looked at was the scale-up factor. So notably, the Jameson cell has a 1-to-1 scale-up factor, which reduces error when you're sizing up from your lab or pilot or demo scale to full scale. Conventional cells can have up to 2.5 to 3 times scale-up factors, so there is more potential for error when you're developing your circuits. So now that we've compared each technology, we want to drill down a little bit more into the comparison with the Jameson cell and also back up sort of what we've said so far in this presentation. So we looked at an independent study conducted by Azenco, which compared capital costs of a conventional mechanical flotation circuit and a Jameson concentrator. And what they found was that there was a 24% reduction in capital costs when you factored in total installed costs. This is due to the footprint reduction and reduction in concrete and steel. We then also looked at the same study which had a power consumption comparison of a conventional circuit versus a Jameson concentrator. And what was found was that the Jameson concentrator actually had a 36% reduction when compared to a conventional circuit. And that's largely driven by the fact that it is not mechanically agitated and also requires significantly less units when compared to that mechanical circuit. Now, moving in a little bit more about the Jameson cell evolution. So the Jameson cell was initially developed in 1989, and it has since gone through 5 different design iterations over 25 years, resulting in a very optimized technology. Now, something that you may not know is that in 2006, the Concorde cell was offered to Glencore Technology by Professor Jameson as a potential technology to further improve ultrafine particle recovery. For 8 years, the Concorde was tested and evaluated, However, the test work showed that there was minimal benefit in ultrafine particle recovery, combined with increased complexity, capital cost, and a significantly reduced operating range, which we've highlighted in this presentation. In 2016, the decision was made to reject the Concorde cell and continue with the Jameson cell development. Since then, the Jameson cell has continued to excel with over 500 installations and is now a very refined technology. It can be installed in any flotation duty. It has dramatically improved ultrafine particle recovery when compared to conventional technology without sacrificing coarse particle recovery. It has a significantly reduced footprint and significantly improved ESG metrics. So now moving into just a final summary. So the current market for flotation cells is obviously filled with many technologies, some of them very mature and some of them starting emerging. So based on what we've looked at today, for ultra coarse flotation, so that's the plus 350 micron range, the Hydrofloat is definitely the most established and proven option, with the NovaCell presenting as a competitor in its early stages. For ultra fine and cleaning duties, the Jameson cell, the Reflux flotation cell, and the Concorde cell present as good options, but the Jameson cell is by far the most established and proven. For roughing duties, your conventional mechanical cell definitely remains the most established and proven. However, the Jameson cell has proven to be an alternative that can bring significant footprint and capital savings with over 80 installations to back it up. So as our ore grades diminish and the ESG demands continue to grow, it's very important to consider alternative technologies to conventional mechanical cells. Glencore Technology has developed the Jameson cell into a very well-rounded equipment that's highly effective in all flotation duties, and we have operating proof that this is the case. Thank you for your time today.
Thank you very much, Carter, and to everyone for participating in the webinar. Our team will be online for a few more minutes to answer your questions.
And in a few days, we'll send you through an invitation to join our guidance hub, where we'll share the slides from the webinar and be available for your questions and discussion. So thank you again, everyone, and we look forward to seeing you in the next webinar, or in my case, in the middle of winter in North America.